Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you for coming. I'm really excited about this talk. We've got some really wonderful demos for you, some great speakers. We're going to be looking at two really incredible applications. One of them, which has been around for a little while. One, which is just coming online. They explore concepts of time and space in extremely large data sets. And first, we're going to hear a presentation from Walter Alvarez and Roland Sekow, who are going to present Chrono Zoom to you. Walter Alvarez received his PhD in geology at Princeton. His thesis research and honeymoon was in a roadless desert in Colombia, living with Guajiro Indians and smugglers. Much of his research has been in Italy, where he worked on archaeological geology, in Rome on the tectonics of the geologically complex Mediterranean, and on Earth's magnetic reversals recorded in deep water limestones in the Apennines. I have to apologize. I'm going to butcher a lot of pronunciations on this one. In 1977, he joined the faculty at UC Berkeley and began a study of the mass extinction at the end of the Cretaceous period. Evidence from iridium measurements suggested that the extinction was due to impact of the Earth of a giant asteroid or comet. And many years later, that hypothesis was confirmed by the discovery of a huge impact crater buried beneath the subsurface of the Yucatan Peninsula, dating from precisely the time of the Cretaceous-Tertiary extinction. He's currently interested in big history, the new field that aims to tie everything in our planet's past into a coherent understanding of the grand sweep and character of history. Alvarez has received honorary doctorates from the University of Siena in Italy and the University of Oviedo in the Principality of Asturias in Spain, where his family originated. And he's going to be accompanied by Roland Sekow, who is one of Walter's students, and has just graduated with interdisciplinary technologies, and was one of the principal co-creators of Chrono Zoom, the tool we're going to show you now. So please help me in welcoming Walter and Roland.
Thank you very much, Donald. And I've never been to a conference like this. I'm a geologist. This is the first time I've ever been to a computer science conference, and I'm having a great time trying to learn your language and making all kinds of new friends. So this is great fun. Roland and I are really pleased to have the opportunity to come this afternoon and talk to you about history, about all of history, and about how it can be visualized using computer graphics. Now, I don't know, maybe some of you had the same experience we did as students in high school and college trying to study history. And I found the topic absolutely fascinating, but it was kind of frustrating because there was this vast amount of information to learn, all in chronological narratives, and there was almost no structure or organization to help you learn it. And then there were always teachers who thought that you should learn very large numbers of dates for no obvious reason. So maybe there could be a better way of teaching history. Let me show you, if I can find my advancer. There it is. Let me show you just quickly an outline of what we're going to do. So we're going to talk, first of all, a little bit about, well, I just did, about history, the fascination and the frustration. And then I want to talk to you about Earth history, which is my field because I'm a geologist. And then we're going to talk about the concept of big history, the notion that maybe all of the past could be studied as a unit in an interesting way that would have interesting results. And then I want to show you what Donald mentioned, which is Chrono Zoom, which is this new tool that we've been developing. That was Roland's idea, and we've been having so much fun with. All right, for those of us who become geologists, history becomes even more fascinating, but also more frustrating because there are all of these wonderful things to learn about, episodes from the past, but in addition, the time scale goes way, way back. So the times, I meant to say that most people think of the Earth as a kind of an inert stage on which human history is played out. But geologists know that actually Earth has its own history, but there's a big disconnect because Earth history goes back basically 1 million times further than human history does. This is a good thing to remember. Human history, written human history, document-based human history, goes back about 5,000 years, and Earth history goes back about 5,000 million years. If you're a precise kind of a person, there's a pretty easily rememberable number. Earth history goes back to 4, 5, 6, 7 million years ago. 4, 5, 6, 7, that's plus or minus 1. We know that one kind of well. All right, so what I want to do now is to just give you one example that I happen to be pretty familiar with, is the dinosaur extinction as an example of an episode in Earth history, just so that you get the idea. There's lots more. In fact, Roland had to cut me off because I wanted to tell you all sorts of great episodes from Earth history, but there wouldn't have been time for Chrono Zoom, so I had to stop. So let me tell you just a little bit about this particular case. So these are the famous, the favorite animals of all little kids, you know, who know how to spell their names and things like that, but they aren't around any longer. And up until the 1970s, nobody had any idea why they had disappeared. Well, I kind of got interested in that problem because I was working in a place where you could come across the historical record of what had happened. As geologists, we find that our record of Earth history is written in rocks. Human historians find it in libraries and documents. We find it in rocks. So you need to go to the right place, the right library, as it were. And this is the medieval city, little medieval town of Gubbio in Italy. It's a wonderful place to work, and it happens to have in the mountains behind the town, in this gorge, are a great sequence of limestones that were deposited on the floor of a moderately deep ocean, grain by grain, as little microscopic fossil shells and clay settled down from the surface of the ocean, accumulated at a rate of about a meter every 100,000 years. So this is really slow deposition. It has a great geological record. And back in here, all of these are beds. It's all, if you walked up this thing, you would basically be going younger and younger in history because the younger rocks pile up on top of the older ones. If you went around the corner back, just out of sight, you would come to this great outcrop that is, shows you where, well, this is an outcrop of the Cretaceous-Tertiary Boundary, and Cretaceous is the last time in which the dinosaurs were alive, and Tertiary is the first time after the dinosaurs became extinct. Now, obviously, there aren't any dinosaurs in these rocks, because these were deposited on the floor of the sea. But there is an extinction here that takes place. That one, okay. So this is the boundary, this is the boundary between the Cretaceous and Tertiary, and if you were to pull a little sample out of there and cut a microscopic slide of it, this is what you see. These are both at the same scale. There's a millimeter. And this is the bed immediately below the boundary between the Cretaceous and Tertiary. Geologists call this the KT boundary. And this is the shell of a little single-celled marine organism called a foram. It's about 1 millimeter in diameter. And these guys, sort of almost as big as this, are present in every rock that you break open from here down for about 300 meters. So quite a few millions of years. So these guys were flourishing in the surface waters of the ocean, feeding on other things. And then when they died, their shells would sink to the bottom and pile up. And you can see there, in addition to the big ones, there's some little ones and some even smaller ones. There's all sorts of sizes of forams in there. And this is much finer material here that is opaque in the microscope because there's too many grains in the way. But at any rate, you cross this boundary and the big ones disappear. You never see them again. And however, some forams, the little ones, did survive. It turns out 3 species of forams survived whatever happened at that boundary. And then later, as you go up above this, they evolve and diversify, and now there are many species of forams in the ocean again. But we came within 3 species of losing the forams forever. All right, so this is a near extinction of forams, and it's contemporaneous with the extinction of dinosaurs. And so the question was, what happened at that time? So about that time, we're talking about 1977, I went to Berkeley and took along a sample of this and worked with my father, who's a physicist, and 2 nuclear chemists, Frank Asaro and Helen Michael, and we decided to measure iridium on these rocks. The reason being that iridium is rare anywhere in the solar system. It's a very low abundance element. Any solar system object has iridium in it at a very low level, but in the case of the Earth, that iridium is down in the core because iridium has a chemical property that it will alloy with hot iron. And so the Earth's allotment is all down in the core, and that means that the surface sediments have virtually no iridium in them at all. So here is the results of this analytical work. And so this is the Cretaceous-Tertiary Boundary right here. This is sort of a background level here. You can see it's kind of about 10 parts per trillion. And Frank and Helen had to be really skillful to measure that kind of abundance level. But you come up here, and right at the Cretaceous-Tertiary Boundary, which is here, you get this huge anomaly. So from 10 parts per trillion, you go out, the graph width is 200 parts per trillion. The peak was at 3,000 parts per trillion. 15 graph widths, it's in the room over on the other side of the hall there. So it was a very striking feature and needed some explanation. And so after a lot of struggling with what might have caused this, we came to the conclusion that this was the result of impact of a large comet or asteroid on the Earth at that time, with environmental results that had finished off the dinosaurs and nearly finished off the forams, and then an awful lot of other species of plants and animals. So this came to be known as the Berkeley Theory, and it was very controversial. I've been through a fair amount of arguments over this back in those days. I'm just as glad they're pretty well over now. But at any rate, we published this in 1980, and immediately people started looking for more evidence. And a lot of evidence was found, and here are 2 of the main lines of evidence. These both come from Cretaceous-Tertiary Boundary levels. And this one from North America, from Montana. And this is a grain of sand, just like a normal grain of sand that you would pick up off of the sea. It's about 1 millimeter in diameter. But it doesn't look like any quartz grain you ever saw under a microscope before, because it has these things that are called shock lamellae in different directions. There's a little bit there, and as you turn it under the microscope, more of them come into view. And those form only in hypervelocity shock. In other words, when an object hits the Earth at, well, in this case at about 30 kilometers per second, which is a velocity greater than the seismic velocity in rocks, which is about 6 or 7 kilometers per second. Basically, the rock can't get out of the way, and it just gets crushed. And that's what produces these rather unique decorations in these things. This one is from the Pacific Ocean. You can see that this was originally spherical. It's been broken open a little bit. But this was even closer to the impact than that was, because this rock melted. It was ejected out of the atmosphere, pulled together as a liquid under surface tension into a sphere, solidified, and then came back down in the Pacific Ocean. So both of these are and this was tested to the almost a ridiculous extent, but these turned out to be just really good evidence for impact at the time that the dinosaurs became extinct. Well, that was during the 1990s, and through the 1990s, the evidence piled up for this impact, but we couldn't find the crater. And it was really frustrating not to be able to find the crater. But finally, in 1991, it was recognized, and it was here. You can see this is Florida. There's Louisiana. Here is the Yucatan, and under the limestone surface rocks there is this buried crater. And the reason it took so long to find it was because it was buried. It was finally found by the Mexican oil company, by Pemex. You can't see it at the surface, but this is a gravity image showing very slight differences in gravitational pull that are different due to different rock densities down there. And you can see here's the outer ring of the crater, and then here's an inner ring, here's a central peak. If you think about what craters on the moon look like, they often have a ring or two and a central crater in the center. So this is very big. This is 170 kilometers across here, which makes it the biggest impact crater we know on this planet in the last 1,000 million years. I'll show you a little bit more about that later. So this was the kind of thing that finally brought it all together, and so this is one of our episodes in the history of life. And as I say, I wish I could show you a lot more. Okay, so that's Earth history. We all know about human history. There's also the history of the cosmos. There's the history of life. What could happen if you brought all of those together? Well, there's a man named David Christian who is a historian of Russian history in Australia, and he's a friend of some people in this room because he's been active with Microsoft as we are. And David invented the concept of big history about 25 years ago, and has been teaching a course in which he tries to tie together all the different things that have happened in the past. And I was sort of thinking along those lines and didn't know what to do with trying to build a history of everything. And then I got in contact, or David actually contacted me. And so I've been teaching a course in Berkeley now for the last 4 years that's called Big History with the subtitle Cosmos, Earth, Life, and Humanity. This is what you do if you're allergic to specialization. But this brings together a wonderful group of students. I've just had a great time. I've taught it for 4 years now. Roland was a student in the next to the last time I taught it. And what comes next, Roland? Is this about the time scales? I think that's what happens. Let's see what happens next. It is about time scales. All right. So here is the biggest problem that we've found in either trying to teach or to learn big history. How do you wrap your mind around these timescales? I mentioned earlier that Earth history goes back 1 million times further than human history does. How do you wrap your mind around that? How do you get any sort of a notion? I mean, we, if we're fortunate, might live 100 years, you know? But human history goes back 5,000 years. That's a lot of human lifetimes. But that's just 1/1,000,000th of the way back to the beginning of the Earth. How do you deal with this? Here are the sort of things that this is. Let me just show you the parameters of the problem here. So here is all of cosmic history. We didn't label this yet, but it should say 13.7 billion years. That's the best number that's available now for the age of the universe. Going back towards the present time, so that's all of cosmic history laid out. Now, if you put Earth history next to it, here's what you see. It goes back 4.567 billion years. So it's about, so it turns out it's exactly a third of the length of cosmic history. And life history is almost that long. We don't know exactly when life started on Earth. We don't have a good record of it. It was probably about 4 billion years ago. Okay, so those are all comparable numbers. But then, if you look at human prehistory, and what I mean by human prehistory is this is a history of creatures that were clearly ancestral to us that had learned how to walk on all four, not all four, on two legs, got that one wrong, on two legs, and who were obviously more closely related to us than to apes. Okay, so that's our definition of human prehistory. It goes back about 5 million years. And then what about human written history? Well, that goes back about 5,000 years. So what we've had to do here in order to make this visible at all is to enormously exaggerate. That's what this star is. These two are enormously exaggerated because otherwise you couldn't see them. They would just be invisible at this scale. How do you deal with this kind of time scale question? Here's something, if you would like to write this down and remember it, here's just some good things. There's kind of a neat thing here. These sort of work in factors of 1,000. So if we kind of define current events as something that happened in the last 5 years, human history is the last 5,000 years, human prehistory is the last 5 million years, and Earth history is the last 5 billion years. That's kind of neat, isn't it? And if you would like to learn one more thing to take home, here it is. That Earth history goes back 4.56 billion years, and for some reason it's got to be a weird convenience. Maybe it was a gift to professors and students. If you multiply that times exactly 3, you get 13.7 billion years, which is the best age we have now for the history of the cosmos. That's the age of the Big Bang. So there's your assignment. There'll be a test on this afterwards. Okay? Excuse me? It's a gift, all right? So I faced this problem, and my students faced this problem. How can we show what the time scales look like? Well, you know, when you deal with many, many orders of magnitude, what scientists always do is we plot things on a log scale, right? Very handy. Here it all is. You know? There's the universe formed in the Big Bang a little more than 10 to the 10th years ago, and here's the present time, and you can plot it all there, but it's just utterly misleading. You know, you try to show this to your students, they don't get any idea from it, because if you look at that, you'll see on this that the distance along this graph from the formation of the Earth to the dinosaur extinction is roughly the same as the distance from World War II to last year. You know, there's some distortion in this this didn't work, okay? So here's another attempt that I tried. This was the best I could do up until a couple of years ago. And that was to draw a whole series of timelines. So in this one, you see, this is all of history from the Big Bang to the present time. So that's 13.7 billion years. And then what we've done is take the last small fraction of it. We've taken the last 2.5 billion years, GA stands for billion years ago, and expanded it like that, right? And then you can keep doing that. So here's where we were. We got to this point. Now we've taken the last 10% of this and blown that up. That's the last. It's off the screen here, but this was 2.5 billion. This was 250 million, and this is 25 million. And you can keep doing that. You can keep going all the way up to the present time. And there's World War II up there, and this is better than the log scale. But it's still not very good, because somehow this minimizes those differences in time scale. And to me, it almost trivializes it. It just doesn't convey the sense of how much time there's been. Okay, so here's what happened. Here's why we're at this meeting. So last year, when I taught this class, Roland was a student in the class. And all the students did some sort of a term project of some sort. And Roland said, you know, I think it might be possible to show this time scale and show these relationships if we used a zoomable version. If we made a zoomable time scale. And so when he presented his first rough version of it, the students loved it, and I loved it, so we worked on it for the last year or so. And so Roland went online, and he found out that the best software that was available to do this kind of zooming was Deep Zoom or Sea Dragon that Microsoft Live Labs was developing. And so we were put in touch, first of all, with Darren Green from Microsoft Research, and then he got us in touch with Bill Crow, who's here from Live Labs, and his group, who are responsible for what you're going to see. They did something really amazing. So this was Bill Crow and is Goldie here? Did she come? Maybe she didn't make it. Okay, Goldie Chaudhry and Karan Singh, Melinda Minch, and Asta Roseway, who's back there. So both of our enormous appreciation to these colleagues for making this happen. So what's going to happen now is Roland's up here to drive the time machine, and we'd like to show you how Chrono Zoom works. So we're starting here as a sort of a starting point at the New Year's Eve on the last day of the year 2000, the last evening of the 20th century, the second millennium. That seemed like a pretty good marker for starting. And so most people here remember what happened that night. Now, if you look at human history as a whole, there's human history written in memories of people who are still alive. And that goes back roughly 100 years. So Roland, if you would zoom out now, and we're going through the days of that month and the months of that year, and there's 2000, there's the 10th decade. There, we're back to the 20th century. So what you've seen now is roughly the time for which history is remembered by people who are on Earth. But of course, beyond what's remembered, there is the history in written documents. And we can do that, and so if you click on that up there on Chrono Zoom, now we zoom out and we go out to all of human written history. And we'll show you some more of this later, but here's a time scale for Egypt across the bottom. Always in these things, old will be on the left, and young will be on the right, and across the top is a time scale that the Live Labs people put in for us. Okay, this is written history. Remember, that goes back about 5,000 years. But human prehistory goes back, no, this goes back 5,000 years. Human prehistory goes back about 5 million years, so let's go out and see that, Roland. Okay, so now it zooms. See, that's disappearing. It's less than a pixel now. And here we have all of human prehistory from about 5 million years ago to the present, but that's only 1,000th of the time there is for Earth history, so let's go and see Earth history. So that zooms on out like that, and now we have all of Earth history on here from the origin of the solar system and the Earth here to the present time. And cosmic history, remember, is 3 times farther than that. So if we can zoom out to that, now you see all of cosmic history. This is the Big Bang out here at 13.7 billion years. Now there's a whole lot of information about the Big Bang that's known, but it's a very inherently logarithmic thing. So if you go to that, you can see this is the things that happened from the earliest point in the Big Bang for which physicists think they have any understanding, through all the things like the appearance of quarks and matter and photons. And that dark age is before the first stars light up. So this is the whole of history all shown on one zoomable diagram. Okay, now if we go out here, this is again all of cosmic history, but we want to just show you 2 or 3 little episodes. So if you'll zoom in, Roland, on part of Earth history, what you're seeing here is the known impact craters on the planet. And the length of the arrow is proportional to the diameter of the crater. So this is the Chicxulub Crater right here, and as you can see, it turns out this is the biggest one we know in the last at least 1,000 million years. There are other pretty big ones like Pompeii and Chesapeake and Manicouagan in Canada, and it's pretty clear from this that in order to get a mass extinction, you need one that's of Chicxulub size or better, because those others did not give mass extinctions. Of course, it may have to do with the fact that Chicxulub, that impact took place on rock that had a lot of CO2 and a lot of sulfur in it, so it may have been sulfur, or aerosols may have had something to do with it. But now I think Roland can show you what's in the rest of this thing. See, off on the left, there are 2 craters at Fredefort and Sudbury. You can go a tiny bit to the right, Roland, there, good. So Fredefort and Sudbury are bigger than Chicxulub, but much older. They are so old that we don't have any fossil record from this time. The fossil record starts about here, and so we can't tell whether those caused mass extinctions. If they did cause mass extinctions, it would have been in single-celled organisms, but we don't have the record to say. So this sort of thing gives you a chance to explore these aspects of Earth history. Okay, now up at the top, you can see we have put in the history of life. And so if we can go over there, yeah, okay, Luca here is not an Italian mobster. Luca is the last universal common ancestor. And so here are bacteria and archaea, and if you go to the right, you can see this is the appearance of eukaryotes, which are the kind of cells that we have. And what we've done in this diagram is all along on the, that'll do, stop. Okay, as you go on the right here, the upper branch is always the one that leads to us. And we've simplified the tree of life by any time there's another group like the amphibians that don't lead to us, we've just shown it as a single line and left out all of the details. But this lets you see and explore and dig around and see how our lineage has evolved. Okay, so there's mammals. Okay, you can go a little to the right now, Roland, thank you, and you keep zooming in here. Okay, there's primates, and if we go further to the right, you see we come over here and we're getting up towards, well, orangutans, there's hominids, and still further to the right. I guess is that there? Okay, all right. So here are humans, and this should say an extinct relatives. And now we have zoomed into the point where we're seeing the human prehistory. And so I won't show you too much here except to point out two things. This is what we call the Mediterranean salinity crisis. About 5.5 million years ago, this was a time when the inflow of Atlantic Ocean water to the Mediterranean was blocked by uplift of mountains in the Gibraltar area, and it cut off the Atlantic water, which is always going into the Mediterranean. And as a result, there was more evaporation than inflow at that time. And so, as a result, the Mediterranean simply dried up and stayed dried up for their 200,000 or 300,000 years. Imagine that, a desert the size of the United States, 2 kilometers below sea level, extending from Spain to Israel. And then, when the water broke through Gibraltar again, it just poured in this colossal waterfall that refilled the Mediterranean. So there are wonderful stories like this in Earth history. And then human history continues. Here's Ardi. You could zoom in on that. Okay, Ardi is a brand new, wonderful fossil. It was described last fall by a team led by Tim White at Berkeley. And she was the first one we know that really walked upright. But you could see that things had not fully gotten to us because although she could walk upright in a kind of a bow-legged way, she had prehensile toes. She could, her big toe was opposable, and she could pick up things with her big toe and move it around. And then if you go a little bit more to the right, you'll see there's Lucy, who's much more modern than Ardi was. She couldn't pick up things with her big toe. And then you carry on here to the left, and we come over through, there's Homo habilis was the first one to use tools, just chipped stones. And here's Homo erectus, who's quite well known. And you go on further, here's Neanderthal, and here is Homo sapiens there. And if we were redrawing this now, we would put our next little box up in this corner, but we were in a rush before getting it ready. So I guess if you zoom out to now to human history, this is what would be in that little bit of a time. Here is the history of Egypt as an example. And if you zoom in on that, you can see that it's divided up into the Old Kingdom and the Middle Kingdom. And here are dynasties, like the 4th dynasty with pharaohs like Cheops and Khephren. And you can build in things like this diagram that show their pyramids. So here was an amazing side benefit of building Chrono Zoom. We built it with a zoomable capability because we wanted to show all of these timescales. And what we hadn't imagined, and turned out to be the case, was we could embed all of this information into it. So you can put pictures in it like this, and I'll show you some more in a moment. But at any rate, this is Chrono Zoom as it was about 2 months ago when I gave a talk at Berkeley. And again, I thank the Live Labs people who put in a lot of all-nighters so that we could get that ready in time. It worked out fine. So since then, we've been going on to think about what to do next. And so if we can go on, Roland, to see this one. This is a first mock-up of what we're calling, what we're sort of tentatively thinking of as Chrono Zoom student. We're going to show you at the very end Chrono Zoom researcher, but this is Chrono Zoom student is to help students who are learning history for the first time and are faced with those problems that I showed you right at the beginning. So this is showing all of human history in Italy. And again, old is on the left and young is on the right. And what we've done here is something which is dicey for historians. We've periodized history. So historians are a little nervous about breaking things up into formally defined periods because, you know, history isn't that neat. But maybe it's worth doing for students who are trying to learn history. So what we've done here is we've periodized all of historical Italy into three parts: pre-Roman Italy, Roman Italy, and post-Roman Italy. And then each of those is periodized in terms. So if you go into Roman Italy, you can see we've broken that down into early Rome and the Roman Republic and the Roman Empire. And then you can subdivide those. If you go into the Roman Empire over there, you can see here is the pagan Roman Empire up to 312, which was when Constantine won the battle of the Milvian Bridge and converted to Christianity. Christian Rome to the right of it, and then here are dynasties of emperors. So if you go over there where Roland has this, this was the best time in the Roman Empire under what they call the good emperors, or the adoptive emperors. And again, what we found is we can embed information in there. So there's Hadrian, and if you zoom in on Hadrian, we found a nice high-resolution image of Hadrian. And so I think it's pretty amazing that that is embedded in image that shows the history of all of Italy. Back out and go over to the left there, you can see here is Pompeii. It's another image from the web, but we hope to be taking our own one of these days. There's Vesuvius that buried Pompeii in the year of 79. As you poke around in this, you sort of feel like you're just in a nice image, and you forget that you're buried in a zoomable time scale. Okay, so now if you back out, I want to show you one more thing about this. Oh yeah, I'm sorry, I was going to show you there. So for example, here's the thing about periodizing. One of the problems that historians have with periodizing history is that there's more than one way to do it. And so what we've shown here in the layer that starts out purple on the left is the Roman Republic periodized on the basis of what was happening in the city of Rome in terms of conflicts between the upper class and the lower classes, and fights for who was going to get to rule it, you know, Caesar and Pompey and things like that. But up above it is a different way of periodizing, and that is the conquests of the Romans, in which they first was a little village in Latium, and then they conquered their Latium neighbors, and then they conquered Italy, and then they defeated Carthage and ended up conquering the entire Mediterranean. So it shows maybe what we'll have to do with Chrono Zoom student is put in different ways of periodizing so that the students will understand that this is not a hard and fast rule. But you can again zoom in on Rome defeating Carthage, and there's the three Punic Wars in which Carthage was defeated. Okay, Roland, if you can back all the way out, I want to show you one more thing. So you can put all sorts of information in it here. So here's our discussion of this question of periodization, and what the problems are, the advantages and the disadvantages. But another thing you can do is you can embed whole articles in it. So here, for example, is an article that I did a couple of years ago with some European colleagues, in which we talk about the difference between how historians periodize human history and the way geologists divide up Earth history, which is quite different. We're doing something different. We're building a time scale. They are trying to make history understandable. But here what's sort of fun. If you back out on that now, you see we can put in all the pages, and here, for example, is a chart from that, and you can see how beautifully with deep zoom you can see the details in there and blow them all up. And the same thing is true of images. So here's a photograph. GSSP stands for Global Stratotype Section and Point. It is the point at which the boundary, in this case between the Eocene and the Oligocene, has been defined. And so what we've done here, sort of as a kludge for the moment, is to just embed a picture of that spike that's literally been driven into the rock. But if you back out, you can see what we planned. We're going to try and take this picture this summer. What we want to do is to do a gigapixel picture from here in which you can start out seeing the whole thing, and you can literally zoom in and seamlessly zoom in on that spike. So all sorts of fun things you can do. And one other thing I want to show you before you go away. Yeah, there we are. All right. Every good scientific paper has references in it, right? Okay, well, here's what we had fun doing. Here's another paper that I was involved in a few years ago. And what you can do is you can embed the paper. So there it is. There's the next one. And that applause is for Roland, I think. But at any rate, at least in principle, you could see how you can have a whole literature tree embedded just right there in Chrono Zoom, so you could go and poke around and read the whole thing.
What happens if your papers reference each other?
I think what I do is I contact a computer scientist, and they help me out. Okay, well, the last thing I want to do now is, and this will just take a moment, we're thinking now about Chrono Zoom as a research tool. And one of the things that we've discovered in working on this is that simply by plotting all of these different time sequences together, we see connections that we couldn't see before. There's a bunch of stuff I would love to have shown you here about the history of continental drift and continents moving around and plate tectonics. And simply by making these illustrations in Adobe Illustrator and bringing things in together, I've learned all sorts of stuff that I never imagined. I've got a backlog now of papers to write about the history of continental drift. So it clearly is a useful tool for researchers, and we've actually been talking now with Donald and Darren and other people from Microsoft Research about where we go next with this. And one of the things we would like to do is to have a situation where you don't have to have somebody spending a lot of time, as I was doing, making those Illustrator drawings, but rather have a whole set of data sets. Basically things that say, you know, that here are all of the kings of England, not France, England, and here are their dates, and you go to a pull-down menu that has a list of all of the data sets that are available, and you just click on that, and it renders for you a drawing of when all of those kings and queens were. And so we have lots of ideas about that, and would be very interested in hearing your thoughts about it. So the last slide, I think, is, oh, thank you, is our thanks to people from both Microsoft Live Labs and Microsoft Research, people at Berkeley. And I would just like to end with a special personal thank you to Roland, who made all of this happen, and who had the idea, who drove it, and has been just a wonderful colleague to work with. Roland, thank you. Is Curtis going on now? We're saving the questions till the end?
So yes, we'll have questions at the end.
Okay, fine.
Great, Walter. That was great.
Okay, so we saw time. Now we're going to take a little exploration of space. And to do that, I'm going to ask Curtis Wong to come up here. Curtis is manager of Microsoft's Next Media Research Group, whose focus spans the linear and interactive media spectrums from television, broadband, and gaming to emerging media forms. I know Curtis doesn't like it when I just go on about him, but I have all this text here.
Yeah, don't read it.
All right. I'm going to make this short. He's a great guy. He's a personal mentor of mine, and he works on really wonderful projects. This is what he's been doing for quite some time. We just introduced the Worldwide Telescope Mars, and he's going to show us some even more amazing things that Worldwide Telescope can do. So please welcome Curtis Wong.
Thanks, Alan. Okay. First thing I have to do is I have to wake my computer up, so I apologize here. A second. I will. Good. let's see, PC2, video. Okay, first thing I learned is you never want to follow Walter. He's really wonderful. So I'm not going to use any slides. I'm actually going to talk a little bit about what you probably never really hear much about. I mean, there's a lot of press about Worldwide Telescope and the new release that happened yesterday. But I'm going to talk a little bit about the history of Worldwide Telescope, why Microsoft would want to do something like this, and how it actually connects with Chrono Zoom and things like that. So Worldwide Telescope is actually something that I've been thinking about for a very, very long time. And actually, it starts back to my early childhood. So I grew up in Los Angeles and in the early 60s. And Los Angeles at that time, of course, had a lot of smog, and in a major metropolitan area, I never actually saw the Milky Way. And then we were kind of a poor family, and so we never really had the opportunity to go outside of the city. So it wasn't until I was in college that some friends of mine, we went out beyond the mountains, and I actually got to see the Milky Way, and it looked actually something like this. And it always stuck in my mind that there were a lot of other kids like me that really never were able to see that. I think 70% of kids in the United States live in major metropolitan areas, and that may be true in a number of other developed countries. And so about 7 years ago, I had this idea to do this thing called the Universe Project. Just because I thought it might come up with some interesting technology. And Asa Roseway, who actually coincidentally worked on Chrono Zoom, worked in my group at that time. And we mocked up some concept sketches of what we thought the thing should look like. And I showed it to a number of people, and they were all really polite. That's kind of nice. Yeah, well, maybe someday. And actually, at that time, the technology was not available to do it yet. And in about 2002, Jim Gray was working on SkyServer, which is the Sloan Digital Sky Survey, was capturing imagery from the northern sky, and they were going to try and put it on the internet and started to make it available to the people. And he said, I really need some help, and if you can help me. And I said, well, I can help you. And he needed some help building a website, so I helped him with the website. But it was always in my mind to do something more. I said, Jim, just having the imagery is just the beginning. I mean, a lot of us have seen these beautiful pictures in those days, of the Hubble. They weren't so good in the beginning, but, these beautiful pictures of the Hubble. But most people had no idea where they were in the sky, how big they were, and what's actually going on in them. So I felt that in this environment that I wanted to create that we called Project Universe was a way to integrate story and rich context as well as connections to information. And that was the architectural metaphor for Worldwide Telescope. And so the idea of the sky is something that I wanted to use as a spatial metaphor. I mean, how do we know where we are in the Milky Way galaxy? Well, if you look at this view of the Milky Way here, one thing we can do in Worldwide Telescope that you can't do in the sky, of course, is because we have the Earth underneath us, so we can't see half the sky. But if you follow the Milky Way around, you see that it gets a little bit fainter, and then, yep, it's sort of barely visible. Then it gets a little brighter and brighter and brighter, and right about here in the brightest part, right where this teapot of Sagittarius is, it's the center of the galaxy. So if you're looking at this disk all the way around, you say, okay, I guess we're closer to the edge. We're actually about a third of the way away from the edge of the Milky Way. What you're looking at here, when we're talking about visualization of big data, this is a very, very large image. It's a terapixel image, a trillion pixels. And if you haven't seen Worldwide Telescope before, one of the things you can do is you can just start anywhere and look at a fuzzy patch and then just keep zooming. And you notice that we're streaming the imagery in real time. And that's sort of one context that I'm talking about here. So if we're looking at this view of the sky, down here in the lower right is a presentation of what our context is. We're at the center of this ball, this celestial sphere, and this yellow rectangle is this field of view that we're looking at. And that's actually also reflected by this blue rectangle here. And as I zoom in, you'll see this little rectangle change as you go further and further in, and so does the blue rectangle scale as well. This shape in here that's not necessarily obvious is actually the shape of the boundaries of the IAU constellation boundaries. That gives you some context there, but I don't usually like to show that. So another thing here is a way to provide a level of context for astronomers that typically they didn't have before. In astronomy, like probably other disciplines, they tend to focus on sort of their specific area of study, and they don't always get the larger context for that particular object. So in here, what we tried to do is bring in imagery from all of the different telescopes that we could find, both Earth and in space. And in here, this example, it relates to imagery for the whole sky. So we're looking at a visible light view. But if you wanted to see that same portion of the sky in, say, the glowing hydrogen, you could see that. You could go over to, like, this is X-ray, so you could see what the X-ray view of the sky is. In fact, if I select X-ray, I can make that as a foreground view, and we can go back to our digital sky and make that as a background view. This particular bright spot in X-ray is a very hot object. It's actually a supernova remnant from about 5,000 years ago. And what's kind of handy about having two different layers there is you can compare between the X-ray and the visible. So as I zoom in, it maintains that spatial context. And as a result, you can see the boundaries of the heat signature are pretty well revealed by the physical debris clouds from the supernova remnant right there. If I were to switch this background layer to hydrogen, I'll set that as a background layer. You can see what the supernova explosion did to the nearby hydrogen. It compressed the clouds of hydrogen along the periphery boundary, and you can see the radiant energy from the compression of the hydrogen. But let's go back to scale and context. So I had mentioned before about this idea of story. So in story, we really wanted to, like with Chrono Zoom, you want Walter. You kind of want Walter in a can. Wherever you're going, you want Walter to sort of explain it to you. And Walter's kind of busy, so that's really hard to do, and we've got to figure out a way to do that. And so what we did with Worldwide Telescope is to create this idea of an authoring engine within this that was analogous to PowerPoint, where you could create Walter in a can. And so there are a number of tours in Worldwide Telescope that allow you to do those kinds of things. I'll give you an example here. This one is, actually I'll pick a different one for this particular purpose. I'll pick this one. This is always my favorite one. And I'm going to pause it and sort of explain the context of this tour. So this tour was done by Alyssa Goodman, who's a professor of astronomy and physics at Harvard Center for Astrophysics. And if you add up all the people that have read Alyssa's technical papers in her career, all the undergraduate and graduate students she's worked with, and everybody that's attended every public lecture that she's ever done, and multiply it by an order of magnitude, that's about how many people have seen her tour in the past 2 years in Worldwide Telescope. So having this ability to communicate these kinds of stories in this environment is a huge opportunity, not just to inform and educate kids in this country, but Worldwide Telescope is used on every continent on Earth. I mean, including Antarctica. And I guess it makes sense because those guys have 6 months of winter and they do have connectivity. But you know, if you look at the top 10 cities that Worldwide Telescope has used, the US cities are only 3 in the top 10. So it's actually pretty exciting. So let me go into this tour and show you a little bit about why we designed the tours this way. And I'm going to take it off of mute. And, oh, that's a calculator. I borrowed this laptop. All right, where is my audio? Is this audio? All right. Nope, that's still doing the calculator thing. I've got more calculators. I think what I'll do is...
Cameras
there we
that
go.
can see heat, just
Loose
like
connection.
the one that took the picture of this cat. Galaxies are filled with tiny particles called dust that absorb the light from stars and re-radiate it as heat. The dust is actually a kind of smoky haze that fills much of the space between the stars, and even though it's very cold, we can...
I'm going to pause just for a second. Sounded just like a documentary. I mean, there was camera movement, and we were looking at this part of the sky, but you know, I could pause this video, but it's actually not video. It's just a path within this really rich visual data environment. So if I decided I wanted to look at this another part of the galaxy, I could do that. I could see what that galaxy looked like from any other particular telescope in the region. I mentioned this idea of tours. If there are other tours that intersect with this particular galaxy, I could branch off and pivot to another tour. So that allows me to explore ideas that perhaps are epic in scope, but if I come across an interesting object that I want to know more about, I can branch off and go down and explore that in greater detail, or perhaps get back on the bus and continue where I'm going. If I wanted to know more about this particular object, we have this idea of a finder scope, which allows us to go and do research about any particular object. I mean, whether you like or don't like Wikipedia, it's kind of a favorite of kids. You can easily find information about Wikipedia, about that object. But if you were interested in information from the ADS, this Smithsonian Astrophysical database is a comprehensive database of all of the technical papers written about objects in the sky. And what's happening is it's going and done a query in ADS and pulled up the most recent papers, including this most recent one from June of 2010 that happens to mention this particular galaxy. So that's just one sort of example about guided tours. I'll show you another tour that I just cooked up about 10 minutes before this talk. And this shows some of the new capabilities of Worldwide Telescope. Actually, you know what I'm going to do is I'm going to go and I'm going to add some music to this tour, just because I haven't done any narration or anything. That sounds good. I have no idea what this music is, but I think I'll also get some narration. Doesn't talk much about the universe. We'll see what he has to say. And then we'll just press play. Oh, anyways. How's that for juxtaposition?
Thank you so much.
Yeah, thank you. We could go on, but actually I was just going to show, as part of that tour, some of the asteroids. So we're talking about big data, lots of data. So this is actually a visualization of 500,000 near-Earth objects. And they're sort of color-coded by their size. And if you look here, I don't know if you've ever noticed about the asteroids. I didn't actually know this until I actually saw this visualization, but these yellow things are the asteroids. And what they're actually separated by, this thing here in the center, I'm making Jupiter bigger. But these asteroids are clustered at the Lagrange points, which are these little gravitational wells, right around Jupiter. I always thought they were sort of evenly distributed. When you're in elementary school, they say, oh, it's all the way between Mars and Jupiter. It's kind of wild. But what we can do is we can accelerate time here. And you can start to see some of the movement of the asteroids, and they're interacting with each other. And every once in a while, you'll see one of these small objects do all these crazy things going up and down through the planets. That's like 10 million times faster. Okay, so that's sort of our nearby solar system. But what if we want to get the larger context in space, kind of like what Walter does in time? So to do that, we had to build a larger context than we had with the solar system. And so right now, we're just in astronomical units going about outside the solar system. And I'm going to turn off the asteroids here. And what we can do is we can hunt around here for something familiar. Everybody recognize Orion here, right? The 3 stars in the belt. There's the Milky Way. So if we pull away from the solar system, here's Betelgeuse, and watch what happens to some of the stars. It's collapsing, but in an irregular way. It's because the different stars that you're seeing in Orion are actually located at different distances, and you can kind of see that this way. Anyway, so we'll just keep going further and further out. Now we're at about 3,000 light years, and we're about to exit the Milky Way. And so this view of the Milky Way as the bar galaxy actually represents some of the newest information that's from the Spitzer Space Telescope, which has done a comprehensive infrared survey of the plane of the Milky Way. And actually we have that imagery in Worldwide Telescope as well. But let's pull further out where we're talking about 365,000 light years. And we're continuing to go out, and you're starting to see the large-scale structure of the universe. So if we keep on going out, you can start to notice some of the voids and the densities of these clusters. Now I want to point out the shape that you're looking at here. The shape is because of the Sloan Survey. So the Sloan Survey has done the northern hemisphere in this wedge pointing out this way. And they're also starting to do the southern hemisphere in that wedge. And essentially, it's taking the imagery from the Sloan and measuring the redshift for each one of these million galaxies. Now, trying to get some real metadata about these million galaxies, you'd have to ask a lot of astronomers to go looking at all these plates to figure out what they are, and it's kind of a problem to do that since there's only 10,000 astronomers, I think, in the whole world. So some of the folks at Johns Hopkins and others put together this website called Galaxy Zoo, where they did some tests, and they test a large number of the public classifying these galaxies. And they found that if about 30 to 40 people would classify a galaxy, they could be just as accurate as an astronomer's assessment of a galaxy in terms of whether it is irregular or elliptical or rotating left or right and other attributes. And so they're able to classify these million galaxies in just a few years. And that data is actually represented in this visualization for the first time. So as we look at these galaxies in this distribution, I can sort of select these galaxies and sort of go to them. So what you're looking at here is a galaxy cluster called the Coma Cluster. And you can actually see this in the sky. It's above Virgo. And what's unique about this first representation is that it's not using the same cookie cutter image for every single galaxy or the same color. These are made up of images from the galaxy. And while it's kind of a pretty picture, it's actually more than just a pretty picture. If I'm looking at this, I want to know more about this one galaxy out there, hanging out there. I can go look up information from Sloan. And because I didn't remember that this was the actual name for it, here's the image of it, and you can see the spectra, and you can actually download the spectral data. So it's possible for an astronomer or an educator to present problems as a guided tour, to facilitate part of that discovery process by creating a tour and leading them to objects, and then proposing problems that students can use this environment to explore and get access to deeper levels of data. So this, let's take a visit back to Earth. So part of visualizing the universe is just sort of the beginning of this, and that was sort of our first vision for what Worldwide Telescope would do, having a really rich base of imagery. But what we really felt the opportunity was with bringing in lots of data. And so I'm going to sort of switch into a view of the Earth. And much of my work over the past year has been working with a group inside Microsoft called Stream Insight that's looking at how to do high-volume streaming data and dynamic queries and motif recognition. And our goal is to eventually have this hooked up into a deep, rich, interactive geospatial temporal visualization engine, kind of like Worldwide Telescope. But it won't be the telescope per se, it'll be the engine underneath it. So what I'm going to do is I'm going to go and get some data. And I think this is kind of a, let's see, that's to start with. I'm getting some earthquake data. I'm going to get some data from the year 2000, and very soon this will be just a data stream, but right now it just happens to be an Excel spreadsheet. It's got in excess of 50,000 rows of earthquakes. This one happens to be from the year 2000. So So I'm going to go into Worldwide Telescope and paste this into Worldwide Telescope. I'm going to scale this down. And I want hover text to be magnitude. Okay. So now I have all of the earthquakes from the year 2000. But that's just a start. I actually want to get some other data. I want to get some data that's current until now, July 12th, yesterday. And this is about 40,000 rows of earthquakes. Oops, sorry. Turn that down. And we'll put that in there too. Okay, so one thing you might notice in looking at this is as I move this, there seems to be a pattern here. Because in that earthquake data, we actually have depth data. So these are earthquakes that are around the subduction zones. And as we move through here, you can see that there's clearly a pattern of earthquakes within the subduction zones. Right. Thank you, Tony. But actually a better way to look at this is to have a different base image layer. And I kind of like Blue Marble better because it shows you the ocean floor. So if you look here, there's another part of the Earth which has, you can see the blue is a little bit shallower, and the lighter blue is shallower, and the darker blue is deeper. These are some of the deepest earthquakes on the planet, about 500 kilometers. And if we go down here and look at it this way, you can see it a little bit better. This is just north of New Zealand. I had a geologist look at this and say, yeah, we know that. There's a really rapid subduction zone down there. But, we also have the ability to do, to look at time. So you can look at this data over time, like I'm scrubbing through this. Or we could just go accelerate the clock and pick any sort of area. So this is the year 2000 right now that we're looking at. You can sort of see how active Chile is. But suppose I wanted to see this stuff above the Earth. I could just go in here and change the properties, and instead of having it represent depth, I could have it be altitude, and change the scale so that instead of it being smaller as it was, a little bit bigger so I could see it. And we'll take it off of time. So now you can definitely see the angularity of that subduction zone. So I'm going to delete this particular layer. I'll go back and get that. It's just the 2000. I'm going to get the 2009 one again. Just because this past year has been really interesting in terms of earthquakes. Yeah. This area here above Puerto Rico is actually very interesting. There's quite a lot of earthquakes, so we'll take a look at this one. It's a little fast. So you can definitely start to see temporal patterns when you compress a year and a half worth of data into just about 10 seconds. So just like with the other tours that you've seen, we can include data as part of the tour. And I haven't shown you anything. We can put in text, graphics, animation, imagery, a lot of other things that you can just imagine. So this is just the beginning of some of the capabilities that we're hoping to have widely, but also with streaming data as well. I know there's going to be, I want to save time for questions because I had some myself for David, and I'm sure you have some too. So I'm going to just end it here, but thank you.
Thank you, Curtis. So yeah, I'd like to open up the, I don't even have to tell you guys, you know what to do. Here.
Hi, Justin Reed from University of Buffalo. I love the research function of the Worldwide Telescope, and I'm wondering if there's something similar built for Chrono Zoom, excuse me. Yeah. In other words, can I, click on a particular part of the timeline and gather research from it automatically? Also, is there a layering function so maybe I could build my own periodizations over whatever's given in the thing? So in what ways can people collaborate in Chrono Zoom?
Well, we certainly hope to get things like that into it, but I think it was pretty obvious from what you saw how much further along Worldwide Telescope is than Chrono Zoom. But yeah, we're looking for ideas like that, and sure, we have the idea to have various different layers so that you could. One thing that would be nice would be if, say, supposing you want to compare the history of Spain and Italy during a particular time in the Middle Ages, it would be nice to be able to bring up each of those and then grab them and sort of pull them up so that they were adjacent to each other. Obviously, you wouldn't very often want to slide them this way because then you'd get the time wrong. But if you could just move them up and down, then you could bring in whatever you want. And Roland intends as soon as possible to put in links to Wikipedia and other sources of information. So yeah, there are all sorts of things. And I must say, watching that amazing demonstration by Curtis, I was just inspired and got so many ideas of things to do. Yeah, do let us know your ideas about things like that.
I've got a related question about Chrono Zoom, and that is about user-contributed data. And if you've thought much about how to incorporate that, because there seems to be so much more that could be included within Chrono Zoom, much more than you or any other single individual could put in. It could be a great tool.
Yeah, that's one of the problems that we're really thinking a lot about now. What do you bring in and how do you bring it? Now, Curtis has an advantage in that so much of what he's brought in is already available in geographically or sky area located images. So much of what we want to bring into Chrono Zoom is not in any form that's very easy to use. It's in a book that was written in 1957, and is a chronological narrative. And an awful lot of that, I think, has to be just sort of dug out by hand. So I fear it's going to be a very labor-intensive procedure, and we're worrying about how to do that. The other thing that is where do you get your information from? So what we'd really like to have would be as much as possible peer-reviewed information, historical information from professors who are authorities on that particular time. But maybe you won't be able to get very much information very fast. So maybe you should be able to say, I want the information from academic authorities, and okay, now I want all the stuff that's from Wikipedia or that maybe is brought in a wiki-style approach. And you ought to be able to make your own drawings and put them in as well. So we're not nearly as far along as that.
But we're working together.
Yes. think how the two will be able to tie together. I mean, you could say, okay, I'm going to go into Chrono Zoom, and you look at the history of the cosmos, and you discover that you can actually see the history of the early universe by looking in the Hubble Ultra Deep Field and seeing galaxies that you're actually seeing them as they were 12 billion years ago. So that could lead you right into Worldwide Telescope, or vice versa. So we're just beginning to think about how we can tie these together.
Take a look at the literature on volunteer geographic information, because we're handling a lot of the trust, reputation, recommendation, and accuracy issues. So we're on that kind of issue of user-generated content at the moment.
Could you get in touch with us so that we...
Yeah. I mean, this is so awesome, because I had no idea that georeferent grids could become zoomable referent grids. So it just opens up a huge well of possibilities. And a couple of suggestions might be doing something like data cubes for the ZUIs, so you could handle the multiple conflicting assertions of historians, so you could stack them.
Yeah.
And another thing is, one of the big advantages of the Worldwide Telescope is the kind of the inset orientation map. You really need that with ZUIs, because you kind of get...
With what is that word?
With these little orientation or inset...
ZUIs?
Zoomable user interfaces.
Thank you, yes.
So you need some kind of orientation. And lastly, if we could, on something like Bing Maps, you have attached not just static X, Y, Z, and T, but methods. Oh my God, we could do agent-based models on digital Earths.
Oh, those are wonderful ideas. Could you get in touch and just talk to Roland afterwards, and let's be in contact? That's wonderful.
Roland will take care of it all.
Yeah, that's right.
Here. Are there emerging standards for the generation and sharing of this kind of data? Curtis, you probably have looked at that because of the many different data sources you're gathering into the telescope. But
well, fortunately, we were lucky, and about 10 years earlier, there was an organization in the U.S. called the National Virtual Observatory, where they were trying to look at all these disparate data sets and how do we integrate them together so they can make interoperability, interaccessibility a lot better. So I think, Walter's alluding to that problem. It is a very, very big problem.
is there a place where that discussion is happening?
Yes, now there's an international virtual observatory organization, but that's just within astronomy. I don't think there's a general area for other data sets. I want to put in just a little bit of plug for what you were saying. This is Abel 1685, and what's wonderful about this is this is actually a gravitational lens. And so a lot of what you're looking at here is the lensing here on the edges is shaped by this dark matter in the center. And these galaxies here are about 5 billion light years away. These galaxies here are about 10 billion years old. And the reason why they're kind of scraggly, aside from being warped by dark matter, is that these are irregular because they're galaxies around the time of the formation of the early part of the galaxies. So you're looking at 2 points in time, 5 billion and 10 billion years ago. So it's a way to kind of look at 2 parts of the timeline.
Yeah.
So both presentations were incredible, absolutely amazing. Both have a very sophisticated browse metaphor. I think maybe a flip side of the coin would be a very sophisticated query metaphor. So I know what I'm looking for, but I don't know where in space it is, or I don't know where in Chrono Zoom it is. Have you given some thought into how I can answer those kinds of queries and what the interface might be to support that?
In our case, I think we've been thinking more of that more as an advantage rather than a problem, because there's so many ways that you can search for things if you know what they are. I mean, if you know that you want to find out about the Battle of Las Navas de Tolosa at 1212 in Spain, you go to Wikipedia and you find it. But supposing you don't know there's any such battle, what we've been thinking about, one of our sort of little catchphrases is that with Chrono Zoom, we think you'll be able to browse history rather than digging it out bit by bit. But surely it will be important to have sophisticated search functions too. At the moment, we don't have enough information in it that that's a problem, but hopefully it will become one.
Search and browse, you need both. If you don't know the question, search is useless, or what to ask for. But in browse, where do I look and what am I looking at? So they should be together. I mean, combining Wikipedia in terms of searching something and connecting it to context, but also context connecting it to specific information like Wikipedia. Oh, I just put in Abel up here, and it pulled up all the things where Abel came up, and then any of their visual examples, I could click on any of them, and that's what zoomed us to this particular image.
All right. Right here.
Yes.
Sorry, Ken Perlin, NYU. In some of the earlier work we did in zooming interfaces, my student David Fox came up with this great phrase in 1992, semantic zooming, which should be really useful for this. If, for example, when you zoom in and you see a paper, the first time you see it, when it's far away, you see an iconic representation, for example, the title in large text or something, and then that gradually fades out and you see more and more detail. It turns out when you're browsing, that's a really useful way to help people discover things if they haven't seen them before.
That's a beautiful idea. Really nice, yeah.
So we're out of time, so I'll wrap it up. I encourage you to talk to Walter and Curtis at the reception. But thank you so much, and if you are interested, please talk to us. Yes.
Hi. Thank you.